is about the survey over computational approaches to cognitive science. And, the purpose of cognitive science is understanding the mind as contrast to understanding the brain. And it's very easy to understand, to discuss what the mind means and what understanding means if we adopt the neurodogma. That is, if we think about how the mind emerges from the brain. I'm going a bit fast because this is what I just said, right? So in the neurodogma, what we can think of the brain setting up cognition, and a very trivial kind of way of looking at that is to say that the brain receives sensory inputs from the world, which transform physics, things outside the nervous system, the mechanics of the limbs, photons from surface and visual surround, sound waves and all these things, into neural stuff, into the activity of nerve cells and activity in the nervous system. So it's an interface with the outer world in a sense. And conversely, the brain generates behavior, which really ultimately always means movement, right? Even speech, of course, is movement. I mean, sound waves are generated by moving, certain muscles and controlling your glottis and the articulatory apparatus and all that. And so that is transforming neural things, neural stuff, into physics, into physical things in the world out there. And so everything that is between those two is cognition. The properties of that are the properties of the mind. And so you could say there are some links between the inputs and the outputs, or the generated behavior, that are very trivial, and people then hesitate to call that cognition. So these are things like what people call reflexes or fixed action patterns. And then the notion is the more complex this link is, the more invariant, distant, or the more abstracted from the sensory motor details the structure of that relationship is, the more cognitive is the system. And so this afternoon, Daniel Sabinas will make an exercise with you where one can put one's finger on that. In the Breitenberg vehicle, you can actually look exactly at the sensory and motor dimensions, and then look at complications. Where does the system, for instance, first begin to make a decision, or does it have memory and things like that, very concrete, in a very concrete form. So that is an approach to defining what the mind might be, the emergent properties of this nervous system that's coupled to the world through sensors and motors. The other question is, what does understanding mean? And that's not anywhere as obvious as you might first think. And I want to first spend a few minutes here on clarifying some notions about that. And then I'll come back after a survey over approaches and discuss that again. And it might be interesting to see if that then makes more sense to you. So one problem with understanding is that the mind as such, so the ensemble of your thoughts, for instance, of your decisions, of your thought process, inferences, and so on, the ensemble of your behaviors and even your brains are not actually reproducible. So in terms of scientific assessment, that's a problem, right? The brains and the behaviors are different from individual to individual. They're different from one moment to the other. When you listen to a lecture like this, after that, your mind has changed, as has your brain. And some of these differences that occur are permanent. They, after you have learned something, your brain remains different, is consolidated in some sense. So all of that means that a scientific approach to understanding the mind or the brain cannot consist of just extensive description, of just listing everything. And you'll see it's not something that's universally agreed upon, but at some level, certainly extensive description as such is not useful, because these things are not all reproducible. And to deepen that a little bit, I want to make a contrast between what understanding means in physics and what understanding means in biology. I'm taking biology because the neuroscience is close to biology. I have actually these ideas from Feynman's book, The Character of Physical Law, which I highly recommend. And he draws this contrast between physics and geology. For some reason, he takes geology as that other kind of science that gives more emphasis to description. So a brief excursion what understanding means in physics. So you all know Kepler's 3 laws of planetary motion. I presume maybe you don't remember them in detail, but they exist, and they are often cited as the archetypical physical law kinds of laws in that they constrain what is possible for planets that go around a sun. Certain constraints they all satisfy. You call them law. You could formalize them as saying they are relationships that enable prediction. So, for instance, one of those laws, remember, says that if you give me the orbital distance of a planet, I can tell you how long its period is, how long it takes to go around the sun once. It's actually a crude approximation only, but that's the nature of that law. That's capturing a constraint. So it says that not all orbital periods are possible. If you have a certain orbital distance, then the period is given. I don't know if you know that Kepler himself was trying very hard for many years to find another law that would explain why the planets at these particular distances that are observed, like Mercury and Venus and Earth and so on, and so something known about their distances approximately. And he tried to find some regularity that explains these differences. For instance, he used very complex solid bodies and sort of try to find some numerical rule, or how many bodies of a certain number of surfaces that maybe only every even number appears, some regularity like that. And that failed. And today we say there is no such law. We just say it's a question of initial condition. It's the history of the solar system when these planets formed. They had certain densities and velocities and so on, and that led to the planets that are essentially condensed interstellar gas, and actually not interstellar, condensed gas from that gases that emanate from the sun, and just the process of them cooling and condensing led to these particular distances. And the proof for that is that today we have observations of other planetary systems around other suns where the distances of the planets are different. So there is no particular rule that constrains the possible distances around the planets. We can never be sure, but that's what we think at the moment. So it's not trivial that there is something lawful. That is, we would say the relationship between orbital period and orbital distance is lawful, but the orbital distance as a function of ordinal number of planets, that's not lawful. That's just can describe completely planetary system around the sun, and it will be different from any other planetary system. It's not reproducible in that sense. And so that reflects the more general idea that physical systems per se are not reproducible. I mean, you're not going to make a list of all the positions and velocities of all the particles that you could measure, because that doesn't make sense. You call that initial conditions, and they're not constrained. But there are laws. That's the strength of physics as a science that has found such laws. And in some logical sense, they have an if and a then part. That is, you need to measure some things and then you can predict something else. It's not actually always unique in which direction you can do that. Very commonly, we think of time, that you take an initial condition, predict the future, but you could just as well take the future and predict the past if you want, logically predict it, not temporally. And we sort of have a scale of laws of that nature, where those laws where there's a very general if clause, so that covers a lot of different cases, then that's a very powerful generalization. And then we call that really understanding. That is something deep. If the if is very, very special, then we don't think of it as so powerful. There's actually another idea that there would be connections between laws. That's sometimes what physicists sometimes mean when they say explain, where you take one law and derive another law from it or some aspect of another law, and then you say you explain that law. For instance, explaining friction by thermodynamics would be an example of that kind of thing. Now, in biology, there's no ultimate difference, but there is a sort of a practical difference. So one difference is that organisms are somewhat reproducible. That is reflected in taxonomy, that we can name different species, and we do that, for instance, for plants. Some of you might know there are these books that list the number of characteristics you need to uniquely classify a specimen as belonging to a particular species, and typically 5 is enough, up to 7 sometimes. And when you do that, let's say you have these, characterize the plant by its leaves and the form its seeds take and so on, then you can predict other things about these plants. So in that sense, it's a law, like the tulip, has certain shapes and certain features, but it's a very, very narrow law. It doesn't really generalize. It just really just says that tulips are always like that. They have certain properties. So you could say it's a large set of very narrow laws, and that capturing that is then what is called extensive description. For a very long time in biology, that was a primary practice to accumulate a lot of detailed descriptions like that. And it continues to be a practice, for instance, in a lot of molecular and cellular biology, not so much in systems biology, perhaps. And that touches cognitive science, because if you look at the brain, for instance, at the level of neurotransmitters or of particular regulatory mechanisms, then you can actually have quite reproducible mechanisms that, in retinal cells, certain things are happening that are not happening in other cells, and so on. You could try to seek the laws of the mind at that very detailed level. Now, neuroscience is inherently conflicted about that. I always argue it is that the dividing line between these two types of understanding. So as was hinting, at the molecular and cellular level, the biological tradition is effective because there are reproducible patterns there. At the systems level, not so much, because the system level is actually connected to behavior, and behavior is depends on history. There's learning, there's context, environment plays a role, and so on. It becomes much less reproducible. In fact, one could say that psychology is, in a sense, more physics-like, because in psychology we know that behavior is not reproducible as such. There are so many factors that are not per se constrained. Individual differences, learning, even culture, and context, that it would be very difficult to say that you only have to measure a handful of things and then you can uniquely predict what someone will do. And in fact, psychology has a tradition. It arose initially as sort of in physics style. Psychophysics, I'll have a little module on that in a moment, was very much aligned with physics that way. So I'll go there in a moment. I want to give you a pointer for those who are interested in these sort of things. There is a very interesting philosopher who's unfortunately already dead. I still happen to have met him, Robert Rosen, who glorified that kind of idea into something really quite mind-boggling. So he talked about simple versus complex systems, and essentially argued that in complex systems, there would be constraints, but you can't really identify them. You can't really find the laws. And the reason for that is that they mix the lawful and the unlawful stuff all the time. And so the metaphor was that things like learning, behavioral adaptation, cognitive flexibility, and so on, make that something that's not lawful, just like what the environment you were confronted with, then is now incorporated into your mind, and now is a property of the mind, and in some sense a constraint, and becomes lawful. And so you can mix that. In physics, physical systems would be simple in that it's always the initial position and velocity that is unlawful, and then the future position velocity that is lawful. I can't go too deep into that, but that's like a really interesting teaser. He uses Gödel's theorem to construct systems which are constrained, but there's no prediction possible. Kind of very fancy. Now, what I want to do in this lecture is illustrate different approaches to understanding the mind, just some, conceptually, to sort of sharpen your understanding what theory is about, mathematical computational theory is about. And I'll come back to my intro here at the end, talking about laws and what ultimately understanding might mean. So I'll briefly talk about psychophysics. I'll talk about mathematical psychology as sort of the modern form of that. I'll try to illustrate why it's useful to make these models in mathematical precision. I'll talk about different levels of modeling, these so-called Mahr's levels, and one of those is, computer metaphor, the information processing paradigm is sort of a reflection of that. I'll briefly talk about cognitive architectures as sort of the most developed part of that tradition, and that is in contrast to connectionism, which is maybe today much more dominant. And then lastly, very briefly about computational neuroscience, sort of the more reductionistic version of connectionism. So that's a very quick ride through a whole field. So it just gives you a flavor of things, of course. So as I hinted earlier, psychology began in physics style. In fact, Helmholtz was a very influential early psychophysicist, and he was a physicist who contributed importantly to physics. And so these early psychologists looked at laws, in the sense of physics. Typically, they looked at laws that somehow link the external physical thing and the internal subjective thing, the subjective state they measured through us, through experience, asking people to tell us what they perceive or think or estimate and so on. So they measured the conscious mind, right? Consciousness is quite accessible to experiment, unlike some myths about that. You can just take measurements on that by using psychophysics. So here's just a classical example, Freshness Law, where you're asking people to estimate the magnitude of some stimulus. It's very intuitive, they just have to give a measure, and they can do that reproducibly. And once you give them a scale, and they have to show that on the scale. And you can look at how their judgment, this is here on the vertical axis, depends on the physical intensity of whatever it is. Here in this case, there's a brightness measurement for visual percepts and a loudness measurement for some other, for sound. And it doesn't actually matter what the absolute scale is. The interesting dependence is the change with the physical thing. And this is a log-log plot. So you see that there is a power law underlying that, a characteristic power law, which you find in very many different domains. This is sort of one already very general kind of law called Freshness Law, where you take all kinds of different physical entities, vary in a intensity-like variable, and ask people to make a judgment, and they have this power law dependence with different exponents. So what that does, it's a law in that it says you're not really free as a nervous system to choose just any dependence. There is a dependence that's characterized here in this case only by two parameters. You could say the offset of this curve and the slope of that curve, which translate into the exponent and the factor in front of the exponent in the original non-logarithmic scale. And so that could also be viewed, a law could be viewed as data compression. You could say, if something is lawful, I don't have to list all the data points. I can actually compress all the data points into just a smaller number of parameters. For instance, the laws of motion that you're familiar with, of falling stones on, you can compress by just having parameters like the gravitational constant and the initial position, initial velocity of a particle. And that can then be, from that you can generate the whole time curve. That's a form of compression. And here you could say, any kind of measurement that you do where you vary these physical properties, that you could compress that just by these two parameter values, the offset and the slope. And that is sort of the mindset from which mathematical psychology was developed. So mathematical psychology continues to exist as a discipline, is sort of the modern extension of these ideas. And it's very largely this idea that you would find uniquely identifiable sets of parameters by postulating models that do data compression and therefore capture constraints. And the mathematical psychology does this quite rigorously and has some real very good link to statistics to make to make exact what it means that the parameters are uniquely estimatable, that there's no arbitrary aspect in the fitting. So he can give you an example of a very popular mathematical psychology model. It's a model of decision making. For instance, in typical cases you would have, let's say, a two-choice reaction time where you have to maybe classify a stimulus, and there would be one response that's the correct one, another response that will be, let's say, the incorrect one if you have a binary choice to make. And the model is mathematically framed as a diffusion process, so mathematical model of Brownian motion, where you start the diffusion process along a decision axis at some location, and then at every moment in time, the system gets a random kick. The variance of that distribution from which these kicks are taken is one parameter, and the width of these distributions, and the other is bias. Is it more likely you get a kick up versus a kick down? If you have no bias, then you would just have pure random diffusion. If you have a bias, it will be more likely to go to the correct response than to the incorrect response. So this bias term is a second parameter. So that's called the drift term. And the third parameter is how far the boundaries are from the initial point. It turns out these are only two parameters. You can either vary where the initial point is and the amplitude, or various ways to parameterize that, but there are two parameters that essentially capture how far your initial state is from one boundary and is from the other boundary. So you have a total of 4 parameters, and then the observation would be that that you make a certain choice and at which time you make it. So the time would vary randomly from trial to trial, and you can make 2 responses, the correct or the incorrect response. And these probability distributions, you repeat this many times. There are cases where people have repeated that 10,000 times in individuals. Have a very dense data set that reflects the probability of a certain reaction time, the time you need to make the decision for the correct choices, and then the same for the incorrect choices. And you can try to determine these parameters to fit these distributions, which turns out to be quite possible and quite precise. And then you have this data compression, right? You can characterize a decision task in terms of these parameters. That's pretty much what it does. I don't think it does more than that. For instance, it's not really a process model of how the brain does that, even though there is some modern use or abuse of these ideas in neuroscience. It's not a reasonable idea of how the brain does that, because you have very much unexplained ideas. Even if you think these decision axis is some neural activation, you have to say, how come that it is reset here? How come that there is a mechanism that when it reaches a particular level, there's a readout? How do you vary the position relative to this result? What happens when it goes to the threshold mathematically? When a random walk goes through a threshold, it would go back below the threshold again with very high probability. In fact, there is in the mathematical idealization of independent stochastic perturbations, there would be infinitely many threshold crossings around any threshold crossing, one of those mathematical extrapolations. And so it's not reasonable as a model of how the brain actually does it. It's a model of data compression. It says some regularity in how this is done. And as typically happens, people then get very familiar with a model like that and think in these terms, and maybe sometimes confuse that with something that actually happens in the brain. So that's an industry that is a whole discipline that has approached different parts of behavior in this way, and often using different mathematical settings, because the main criterion for these different settings is not so much that they capture something about the brain, about mechanism. It's more really that it does the data compression. That is, there are unique parameters, values that you can determine to characterize the performance in one particular setting and contrast it to the performance in another setting or in another individual, and so on. it captures the regularity of the law. In practice, this approach is quite limited because of this demand of being, having these uniquely identifiable parameters and, being capable of pulling out the differences between different skills and individuals and so on. And so it's only a small number of phenomena that have been studied this way. And so sort of the field is sort of a collection of phenomena like that, which are not very strongly connected also to each other. And that also makes that these models of mathematical psychology are very much based on isolating particular phenomena, like the origin of psychophysics was. I was saying, I'm just looking just at the detection of light, or just at the onset of a decision, or maybe I'm just looking at how, the utility of a decision and so on. And I'm not looking at the sensory motor part, or not looking how it's connected to experience, to learning, and always study all of these aspects separately. And therefore, it's not obvious how models like that can be integrated into more comprehensive models that would explain both how participants perceive and how they maybe engage their motor system, and how memory plays a role, all in the same task, which would, of course, be really the case for an actual person doing that. All kinds of faculties play a role when you make a simple decision task. And that also reflects that doesn't really take neural principles into account in the nervous system. You do have these different systems engaged in that task, and you would have to know how they interact. Actually, neuroscientists also often don't really deal with integration across different parts of neural function. But it's also not taking neural principles into account in the sense that the mathematical descriptions aren't really constrained by the properties of neurons or of networks. I'm going to skip this example, even though it's kind of a fun example, and just go directly to a somewhat different example. And I want to make this example really to make the point why it is still useful to make these mathematical models. So other than data compression, why does it make sense to really write down a mathematical model rather than have a verbal story, for instance, or a conceptual model, drawing? And there are lots of models like that in the literature, where people make a drawing, have a sort of an image in their mind. They call it a theory, but they are not mathematically formalized. And ultimately, the message is the quantitative aspect is very good to pick up failures of models. And when you make a mental model, you're actually strongly biased to just look at the aspects that are right, and it's not so easy to point out aspects that are wrong about the model. When you try to fit it quantitatively, then you will be confronted with that. I want to give you an example from my own career. I studied with someone called Tjeerd Dijkstra in St. Gielen in the Netherlands. Upright standing in the moving room paradigm. It's a posture sway. It's a very well-known paradigm where it turns out that when you stand upright, you sway a little bit. It's a sort of a mechanically unstable thing, and you have to control all the time your stance. And it's very well known that vision is one contribution. If you close your eyes, you sway more. And if you open your eyes and the world is swaying a little bit, the moving room is that the environment is moved, then you're sort of entrained by that environment. Some of you might have experienced that in a 360-degree cinema. There used to be sometimes done on fairs where you can go and watch a very dynamic movie filmed from inside, I don't know, maybe a very special vehicle or an airplane, and very dynamic pictures, and then you would really feel the pull to as if you were in that vehicle. And the kind of data that people look at there is that they make the room move periodically, and then they look how the sway is entrained by that periodic signal. Something called the inverted pendulum model. It's not so important what the detail is. So mathematically, you can write down a model of that kind of behavior in which you simply have an oscillator that is entrained by some visual signal. And at that time, I was engaged in doing experiments where we varied all kinds of things like the frequency of this drive and tried to estimate these system parameters. It's really the eigenfrequency and this damping, two parameters The only thing that you can fit here, there's actually a coupling strength here, but that in some sense, that's not a real fit parameter. And then see if we can fit the data, and that would confirm this image of a pendulum being driven. And it turns out, no, it's not a good fit. So you see the dashed line is the fit, and the solid line is just a curve fitting to the data points, which are these different asterisks here. And you see there's something systematic wrong about that. This uses phase and gain, but you can see with the naked eye, there is some systematic mistake in this model. And that was actually interesting. We always say it's most interesting when the model is wrong. It's a quantitative thing. If you just know that as you increase frequency, gain is going to go down, then the model and the data are sort of the same. It's just not going down exactly like predicted by the model, but qualitatively it's right. And also know that the faster you go, the more lag is there. The more you're lagging behind the visual input. That's also sort of makes even common sense. And that is qualitatively true, but not quantitatively true. It turns out that this is a little bit more difficult to explain. It turns out that one can understand this difference. What happens here is that in the experiment, you vary the frequency of the drive. That is, you're showing the person on the screen a moving room that moves with different frequencies. And the model fitting is based on assuming that these parameters are constants. This is the eigenfrequency. So how, if you have no drive, there will be some spontaneous oscillation. That will be your eigenfrequency. It's related to the stiffness of your muscles, how strongly you resist perturbations. And it turns out that the data, the lack of fit comes from the fact that this constant is not constant. It actually varies with that external drive. So what actually happens is that people, when they're driven like that, adapt to that drive. Unconsciously, you're not aware of that when you're a participant in this experiment. You're adapting, and that adaptation leads to the curve. So if you take that adaptation into account, then you can actually account for the data. So it's a negative result, a failure of a model that drives you to discover a mechanism in this case that was not contained in the model, and the model, the failure of the model sort of uncovers the need for more examination. If you had just made the qualitative argument, it would have been pretty a good model. And in fact, in this case, we did this in the 90s, as you see, and the model of the inverted pendulum that is coupled to the visual array had been around for 25 years by that time. And everyone was sort of assuming that's a trivial thing that is not worthy of further study. But as we try to make it more precise as everyone else, we discovered it's actually wrong. And there are more facets to that. So models are useful, especially when they fail. And models will often say that. When they don't fail, then they just mean that the assumptions that are in the model are sufficient to understand. That doesn't mean very much. It's actually more interesting when you discover some new phenomenon based on modeling. Here is this adaptation was also something called sensory reweighting. There's actually a major field of research. Actually sort of saturated now, but for a long time it was a very active area of research. We contributed to that field. So mathematically formulated models are useful. I had other examples, but it takes too much time to go through all for us. Now, what kind of models, right? That's really the other question. And there are many levels of description that you could think of for the nervous system, from individual neurons, maybe to these the diffusion model, very abstract kind of description. So it's a tradition in this field to talk about levels that are David Mahr kind of canonized. He was essentially integration. What he was, he worked on computer vision, but inspired by visual properties of the nervous system, or of humans, by human visual psychophysics. And he proposed these three levels, and it's very influential. He died of cancer shortly after publishing this, and some kind of glorification also of these ideas. And I wonder if there's something problematic about that too, but it's a very common framing. And so he talked about three levels. One is the level of abstract computational principle. The other is called algorithmic level, and the third is called the implementation level. And the names have sometimes changed, but this is still how models are very often classified. And you see computation, the top two are actually, in some sense, computation. The algorithmic level is sort of like the implementation of the computation, while the third is maybe the neural implementation. And they're very influential to this day in a way that I personally find problematic. Let me give you some examples and make it concrete. So the computational level is supposed to be an abstract characterization of what a particular behavior or cognitive function or so is about. How is it constrained as a matter of principle? So famous example that's the kind of examples that David Mahr actually came from, is from what is called computational vision. And it's sort of an abstraction of really understanding vision, and a second of saying, can I make some assumptions about the nature of the vision sensor and the nature of the environment and the world to understand what in principle a problem of vision would be a solution to certain problems of vision. So for instance, when you are moving around as an observer, you have a 3D head with a camera in the head, it's your eye. It's a rigid body, that is, your head is moving through the environment. In translation, it has 3 degrees of freedom, and it has 3 degrees of freedom of orientation. It could be your eyeball or the whole camera. So it has 6 degrees of freedom. And you're moving through the world, and the world, let's say, is a rigid environment. It's just surfaces that are not deforming, that are not moving. And there's a light source, which is also fixed, and you're moving through that environment. And so one question was asked, can I track from the velocity field? On your eyeball, there will be, as you move around, the stuff will move. There will be a optic flow. Optic flow is just, the velocity vectors on the retinal surface or in the camera plane of points that correspond to points in the world. It's a question of how you compute the optic flow. The flow field will be the abstract thing for that, and then you have to maybe estimate it from the image. That's a different problem. But if you have that flow, it's a question, could you then determine your ego motion? You have an intuition. If you move left, right, the visual array moves on your retina, and you could maybe estimate your rotation speed from just that, without actually knowing the details of these surfaces, just that they're rigid. And it turns out mathematically, you can prove that you can determine 5 of the 6 parameters given the optic flow, and not knowing anything about the layout, just knowing that it's rigid. That's a mathematical thing that you can prove. You could see only 5 because you could imagine that if you had the same scene and everything was larger and further away, and you would also move faster, it would give the same flow field. So it's like a scaling law, because if you don't know the absolute distances of things, or you don't know your absolute speed, there is a scaling factor that cannot be determined. That's part of the mathematical proof. So this would be an example of a computational principle that you could say, well, maybe I could in principle determine my ego motion from optic flow. There's a serious idea that has some psychophysical support that people can do that. For instance, famous Gibson's ideas of people landing planes by exploiting the optic flow so that they know it's not exactly this problem. So it's somewhat like that problem of knowing when they will touch down, for instance, or stopping a car based on just the flow field. So knowing when the flow field is critical, then you will hit an object in the world. It's slightly a different version of that, but sort of connected. These ideas are, so there's a lot of ideas like that in vision. And another example that you might know is shape from shading. If you assume a certain property of surfaces and you assume a certain property of light sources, then you can compute mathematically the shape from the shading pattern. And that doesn't mean the nervous system will be able to do it. Doesn't explain exactly how the nervous system does it, but it says it's possible in principle. So it poses that as a problem. In motor control, this is a very strong influence. People talk about computational motor control, and they say, for instance, that the movement trajectories of your arm or of your limbs and so on are those that minimize some cost function. For instance, the effort would be the error, deviation from a target, let's say, and the control signal that you need to send, what is called the effort. That if you minimize those, you get the right trajectory. And there's some hint that that might be true, that certain regularities emerge from a principle like that. And there is a very strong influence currently in cognitive science of that nature, based on Bayes' rule. Bayes' rules, this is sort of this is trivial corollary of the definition of conditional probability. But if you fill the different terms in that equation as being priors on the one hand and sort of measurement functions of the probability distribution that captures the transduction property of whatever, however you measure your observation, then you can ask if observers make decisions or estimation, classification or estimation decisions for stimuli of any kind of sort that are Bayes optimal, that in some sense follow Bayes' rule. So if the prior probability varies, will they, in the same sense that are there, will they actually vary their decision based on that? In some cases, people do, and then that's an abstract computational principle. Again, it doesn't say how that's done, how the nervous system knows about the prior probabilities, and how it's sensory information time varies. How do you do all that? And so on. It's just an abstract principle, right? So these principles are quite influential, and you might not have noticed it so far. It has some kind of input-output feature in the sense that their computation has some input-output notion that you have something to, as input, you compute then the answer, right? It's people in this field often don't like to talk like that because the method of computation might be one that is not unique. For instance, it could be an implicit equation. You have to do something mathematically more complex than just a function evaluation. It could be more complex than that, but it is conceptually, it's just some kind of input-output picture, which is one of the reasons why I'm a little skeptical sometimes of that, because a lot of behaviors and thinking happens in some sense in closed loop. In other words, where the sense data you're given or the start data you're given are actually produced by your behavior or even your thinking. And in closed loop emerges some behavior. And that's not easily characterized by computation, but it's difficult to say that in general, because you could make a computational principle that twist that around and still cause, for instance, this optimal control kind of idea is able to deal with things like that. So that's the computational level, quite influential these days. And you might be running into Bayesian, probabilistic thinking a lot, even in this course, I think. Now, the algorithmic level, this was done in the 70s, and maybe then people were really thinking about computer algorithms. And the information processing account. So we have information that you can operate on with programs, ultimately function calling kind of programs. And that would be ways of how you could concretely solve the computational principle. So in the example I told you, how do you actually compute the optic flow, and how do you solve these equations? The equations just say that the ego motion is determined by that up to one degree of freedom, but how do you actually compute it? Can you actually make it work? And it was often then considered a proof of concept that you can do that, even with a computer algorithm that does that, even though that's not like what the nervous system does exactly. So I would say that sort of thought is very strong in information processing and concept of cognition that I'll come to in a moment, which with the cognitive architectures perhaps as the most elaborate form of that. I would say that some connections accounts are also of that nature. They're not actually neural implementation accounts. They're more abstract computational accounts, except they use different kinds of, so rather than algorithms with of a procedural language, they use algorithms in the PDP language, in a sense. In fact, PDP, parallel distributed processing as this one, was started by providing software that implements these networks. And so in the Mahr perspective, all of neuroscience is just implementation. So implementation in a sense, how do you physically do that? How do you, if you have an algorithm that does some abstract computation, do you run the algorithm on a digital computer or do you run it on neurons, for instance, right? That would be, and you could think of other solutions as well. So neuroscientists correctly find that very dismissive. And in particular, you see there's a strong bias in this view to think that lawful things, constraints, really only arise at the highest level, the computational level. They capture laws of vision or of action. And everything else is really just implementation, algorithmic or neural, and doesn't actually give rise to additional constraints and laws. And in neuroscience, people, of course, got quite convinced that's not true. For instance, for nervous systems, there are a lot of additional constraints like homeostasis constraints. How do you normalize? How to make sure that your system doesn't drift? Does it, when you have adaptation to different sensory levels, how does that happen? These are all. So how can you even represent a physical quantity? Because the sensor has unknown parameters that may be changing over time, just as an example. So there could be additional laws at that implementation level. So just consider it implementation isn't right. And I'm actually quite critical of this. So computational neuroscience models could be viewed as being sort of the implementation level in this hierarchy. So again, I think that these levels have somehow enabled people to do work, and that's often then makes them very influential, largely also as a way of justifying that you neglect certain things. So I don't think it's very clear that these levels are really particularly prone to help us discover laws. They're not really captured, characterized by principles, for instance, invariance principles. And they have sometimes the pernicious effect of inviting researchers to ask certain kinds of questions. That's particularly true about these higher levels. And these questions can be sometimes sterile. Sterile really means that they don't give rise to interesting discoveries or don't lead to further questions. They're sort of dead-end roads. We have had waves like that going through cognitive science where, I'm a dynamic systems person. And so there was a time when dynamic systems people were always computing the fractal dimension of any time series you observe. And, then it's 1.3 and then what, it was a dead end road. It didn't really lead to anything else. So that's a risk also of these abstractions. Okay. Now I wanted to elaborate a little more this computer metaphor image. It's called in English really information processing perspective. I think in German Informationsverarbeitung is sometimes meant in a more general sense. So some people will say the nervous system does that, but don't really subscribe to the computer metaphor. When this came around, about Herbert Simon, Alan Newell, are famous names, was about the time of the cognitive revolution. A little later was when artificial intelligence and cognitive psychology were closely allied, and the artificial intelligence very much driven by computing, computer science, was used as a metaphor of thinking about human cognition. And they had this idea of a general intelligence, that there could be some principles of artificial intelligence of which humans are a special case, but you could also build other systems that are general intelligence and so on. And that was all in the notion that cognition is a form of computation, and there are different variations of that. It's not exactly the principle of computation I just talked about in David Mahr, which is essentially really saying that there are mathematical constraints, and the word computation actually is a little bit misleading there. It's just mathematical laws of vision or of action and so on. While the information processing people in that sense were at the algorithmic level, and they talked about computation really in the sense of manipulation of symbols constrained by rules, programs, algorithms. Symbol processing, cognition as manipulation of symbols, that's a definition you will find in Alan Newell's famous book, for instance. So it was, of course, not assuming that there is physically a computer in the brain, which we all know there isn't, but to say that the brain works like a computer once you use this abstract description of the computer manipulating symbols, because the actual computer consists of flip-flops, which are bistable dynamical systems actually, and that are coupled in some way. So it takes a certain abstract description of the computer's function and say that's the right description also for cognition. This was strongly tied, these debates have been partly forgotten now, just because the agents are now very old and no longer so articulate. There were strong debates then about principles that were inspired by this metaphor. So for instance, this principle of modularity, which is a concept very important in computer science, there's called encapsulation. There's an idea that you would have different modules that are computational components, for instance, function subroutines, you could say, and that they have a well-defined interface with the rest. That is, they get an input and they get an output. This interface defines what the rest of the world knows, and how they do that, how they make the function themselves inside, that's not known to the rest of the system. As you know, in programming, that's an important thing, because if you introduce dependencies on the inner states of these modules, it becomes very difficult to make sure that the whole program works as designed. And if you add a module, you have problems that that module needs to be informed about all kinds of things that it doesn't really get through its interface. So that's considered bad computer science to do that. How, is that true for the nervous system, for the mind as it emerges from the nervous system? That was a real research question. And people like Jerry Fodor was particularly engaged in this debate. He used this notion of impenetrability as evidence of that. That is, that you cannot actually get access to the, to properties of certain processes if you're another process. So for instance, that, let's say, memory is not informed about certain sensory qualities, and therefore it's not penetrable. Therefore these properties, perceptual properties are not penetrable. And I would say that debate has also been a little bit sterile, although this problem of modularity is a problem also for contemporary models. And actually the kind of theory I do has directly, has to deal with things like that. So if you think of a neural network, let's say neural network, there are connections, and along these connections, activation or spiking also happens, and that's your interface, right? So any subgroup of neurons cannot know about other neurons other than through the spikes that come in. Actually, there's something with neurotransmitters and modulators and so on that might make that more flexible. So in a physical sense, thoughts like that might be relevant, but functionally, it's a more subtle story. So I just want to make you aware of these terms. That's what was important in this domain. Now, the cleanest instantiations of this kind of thought are cognitive architectures, which were very popular certainly in the 90s, and there's still active work on that. ACT-R is maybe the best known. SOAR is maybe no longer so much used, but still somewhat used, and there are more. And they sort of, I review them here briefly. I have too many slides about that, but I'm going to skip some of those. They are interesting in that they use information processing. That is, they assume that there are really messages that you could send, information about things, which is not, neurons just fire in the brain, so they don't send messages in that sense. You don't know what the spike is about. It's just a spike, right? But here there's the notion that there's information which makes them much closer to becoming actual functional models when you implement them on a computer. But then there are also some elements of them that are sort of brain-like. And it's not easy to sort that out. Actually, I don't think that they really capture constraints. They just describe constraints, but they don't really explain their functional meaning. But that's a question. So in cognitive architectures are, in a sense, describe at a more abstract level what the structure of the brain might functionally mean. Yeah, let's maybe not go too deep into it. So very concretely, I'm reviewing here ACT-R, which John Anderson developed over the years, goes back probably to '83, and some kind of it's a neural model in the sense they're elements that have activation as a variable that evolves in time. So that's an abstraction of neurons, somewhat like in connectionism. That activation is passed on to other elements. The subtle difference from connectionism is that what the elements stand for, the information they represent, that is something that is just fixed. You say this element stands for that, and this stands for this, and so what it stands for is not actually determined by the connectivity. The connectivity just determines whether it is invoked, but it stands for, in some magic way, for a certain piece of information. So, for instance, in concrete models, they take mental arithmetic as a very good model system of a cognitive process. It has rules, it has data, it has various degrees of difficulty, you can measure things about it and so on. And it's clearly not sensory motor, it's clearly some cognitive thing, right? And so in their notion, there are these elements that have activation variables, and they represent things, for instance, a memory of numbers, rules, operations, perceived items, motor commands, and so on. And the weight and so on, that's the subsymbol. So they are symbols, they stand for things. And the subsymbolic aspect, that is that there's some activation that evolves in time that is associated with the symbol, and that tells whether that symbol can do its job or not. So when it's activated, they call it a rule, for instance, is fired. They even say fired, like a neuron fires. Then that symbol that they call chunk can do whatever it is supposed to do. But how it does that, that's not part of the language, right? That's the contradictory thing. So in practice in computer simulations, when you have, for instance, there's an addition, something that could do adding, it gets two arguments, could do adding. It is invoked when it's activated, but how it does the adding and how neurons represent numbers and so on, that's not part of that thinking. That's what is a little bit puzzling always about that. Yeah, and the way the activation evolves is sort of inspired by neural principles. So you have sigmoids there, and you have certain characteristic time functions. That's the idea that it takes about 50 milliseconds to make one of those computational steps, which is sort of, right order of magnitude for what small neural populations do. So there is some closeness to neurophysiology, which is largely used to look at the time over which neural decisions evolve. And the kinds of predictions are always about the complexity of the operations that you have to make, and that then predicts how long it takes, and sometimes maybe also how many possibilities for error there are if you have certain stochastics in there. And you're using then error rates and latencies, how long you take for certain operations, then as the primary experimental measures. That's how these things are compared to experiment. And so they are not so much talking about the contents of what it is that you're doing. I actually had interesting debates with some people in this field when I was still a very naive physicist, where I didn't get how they could be talking about these subtle timing issues, but they're never talking about the contents of what you're actually doing, whether you're making a movement or you're computing numbers and so on. That would, we know that motor tasks are much faster than arithmetic tasks, right? But that wasn't interesting to them. They were just interested in sort of subtle differences between different forms of arithmetic, for instance. So the other level in which there's brain ideas in here, that there are architectures of these different modules that then are supposed to capture brain properties. So for instance, there is some kind of central bottleneck where everything has to go through some central procedural machine where one thing is done at a time. And that is done because we find that humans do have these attentional bottlenecks, that you cannot actually do two things at the same time when they actually at least have overlapping representations involved. And sort of this again is a question, doesn't really explain that, it just describes that, because you could arrange these modules also in a way so that they don't have the attentional bottleneck. And that would work in terms of computation, would work maybe just as well. But because humans have the bottleneck, they also put the bottleneck into the architecture, and then it would be with the question, does that explain the attentional bottleneck? Maybe it doesn't. I'm not explaining this in the level of detail required, but be aware, knowing about Act R is, of course, a whole lecture course, and that's even still scratching the surface. But just to give you the flavor of that, it has a little bit. You can skip that. So here's an example of kind of data they account for, like the time per computational cycle, and they look at different operations that are being done and compare the model to adults and to children, and overall patterns that are reproduced. And these are not very constraining data, I have to say, but that's the kind of thing they do. So it's not incompatible with mathematical psychology, but it's much more macroscopic in its approach. Okay, I don't want to go too deep into that. So today, cognitive architectures still play a role in cognitive ergonomics when you try to characterize cognitive work, like for a driver modeling, what kind of processes you have to coordinate. Is it bad to speak on the mobile phone while you drive? So the theory doesn't predict that per se. It's just, it can model that, and therefore put that into parameters. And there's actually work I was involved in that looks at the cognitive load of a driver, for instance, and kind of is able to measure or to quantify the weight of different sub-processes on your overall processing capacity, for instance. So in this applied sense, they're quite good. There's also, ironically, a sort of a twist in which some of these modules are then mapped onto brain areas, and you use these models to talk about imaging. So when certain areas light up, you say, oh, this must be the memory module that is now being invoked now in this task, and so on. Okay. Now, last two approaches: connectionist models, and then very briefly computational neuroscience. So connectionist models were actually conceived as an alternative, like a revolution against information processing, or against the computer metaphor. And they talked about brain-style computation. It was in the 80s. The PDP was originally a term, parallel distributed processing, as compared to CPU central processing. Ironically, there are parallel digital computers as well. And you'll see in a moment that the PDPs aren't actually quite as non-computational. But it was also an argument against rigid modularity, an argument that functions could be distributed among multiple areas or multiple populations of neurons. But then there are some ways in which it wasn't so different. So this is one of the earliest models. McClellan and Rommelhart are sort of the heroes of this field. Rommelhart, unfortunately, he died recently, and he had a brain disease for a very long time. And Jay McClellan is still very active in that field, a very, very good scientist who's actually very good in discussing about the conceptual commitments, and in no way ideological. So if I criticize some of these ideas, it's not nothing personal. It's just really understanding what the right concepts are. So you see in the original models there was some interesting parallel, and they came from the same origin. The researchers were mathematical psychologists, all of them. And so you see they have neurons, nodes, that are also standing for something fixed. You put the label here to say what they stand for, and then you connect them a little bit more randomly, perhaps in more complex ways, and have many more parameters because of that. And then look at how activation unfolds. For instance, here about word recognition, you would have a layer that characterizes certain graphemes, like simple shapes, and then assemble from them letters. Like letter A would be excited by this grapheme, and maybe that one, and not this one, and not that one, and so on. And then you would have a letter encoder, and then the words would be, driven by the different letters being present. You can imagine how that would work, and and therefore the nodes end up standing for something, and the connectivity between those, again, just says how they're invoked. Now, it's not exactly like that, because unlike Act R, where the nodes stand for something, and how it comes to stand for that is mysterious, isn't part of the architecture. Here it is part of the architecture, that is, these connections from these graphemes, let's say, to the letters, are supposed to be such that this node will come on when the correct graphemes are here at the bottom, without any hidden magic of how it does that. So that's a real step. And that is a step that is pervasive today. You know, deep networks and so on are all about that, about finding the connectivity in these networks that makes that possible, that the nodes stand for the right thing. So networks like that can be scaled into architectures. And by architectures, I mean then complex networks that connect very remote things, so visual input, acoustic input, and let's say cognitive input, to really represent something like words, right? That would be across many scales and different skills and so on, just one big neural network. And that was sort of the ambition to do that, to explain cognitive function from that. The way these models connected to experiment was still largely about timing. So when you look now at the processing, so when the network has, the connection has been fixed, I'll say something in a moment about learning, but when the network has been fixed, it would then have characteristic performance, for instance, a classification task, and you would look at how activation evolves in time. This is time in the network. And then you would compare some interpretation of that to say, well, if there's a significant level of activation, then I'll make the decision, for instance, somewhat like the diffusion model. And then you would say, well, in certain cases, it will be easy. The difference between these activations is large, and therefore you can make the decision easy and early, while if they're more confusable, then they will diverge later and you can make the decision only later. Things like that. So not radically different from the other models. I can't do justice to all of this. Is also, in a way, the universe of networks that through their connectivity arrive at capturing some function is very large. And that includes all the networks that I personally am working with, the dynamical field models, which are a limit case of attractor networks, a special case of attractor networks, which are strongly recurrent neural networks. But the networks that you might be very familiar with are these feed-forward networks, where there's a unique directionality of coupling. When they are called deep, just means they have many, many layers and also many neurons. And there are other differences that have to do with how you fix the connections. So learning means that you have some algorithm of how you fix the connections. That's what used to be called fitting in mathematical psychology, or would be optimization in these computational approaches. And connections often call this learning, even though it actually does take the form of fitting. I'm not going to go into that deeply here. You will have lectures by Zhencheng and Lawrence Wistfeld, especially Zhencheng will be talking about learning, and Lawrence Wistfeld will also talk a little bit about that. And in a way, these learning rules of how you adjust the parameter values of the synaptic connections to be right are really more like fitting. It's very clear in the case of supervised learning, what they call supervised learning, where you know the correct answer and you compare that to the answer the network gives, and that's the error, and you're making a gradient descent, that is, you're changing the parameters in a direction that reduces that error, and you can back propagate that through the network. That was the big breakthrough to be able to do that. And so that is clearly not what happens in the nervous system, where it would require quite a lot of machinery to even be able to detect something like that, like an error. How do you know the correct answer? If you know the correct answer, you don't actually have to learn the whole thing. So there are many levels at which this is unrealistic, but it's very clear what happens in fitting. In fitting, you're changing parameters to reduce the discrepancy of your prediction of something. And even in unsupervised methods, unsupervised methods means often that you're just giving a system a lot of inputs, and it have some rule of how it updates its connections just depending on these inputs. The supervision consists in telling the system, this is an input, this is an input, this is an input. So giving them examples, drawing examples from distributions, and essentially also telling the system when to update. So what is a good example? Which also in the nervous system doesn't really happen like that at all. So one could say that these models in a way capture the statistics of stimulation. So if you get stimuli from a certain ensemble, then the network will reflect that characteristic of that ensemble. For instance, covariation, that, for instance, if you train these systems to classify visual inputs, then these networks will discover that when these visual inputs are, let's say, images from the real world, that the pixels in images like that don't vary independently. They have much reduced variance because the different pixels co-vary, as most of the light comes from surfaces that are somewhat continuous and neighboring pixels, and they have neighboring feature values, and there's certain properties of rigid surfaces that constrain the images and so on. So they will strongly reduce the dimensionality of the original input, and by doing that might extract really the feature that is most discriminative of, for instance, a particular category of object that you want to learn. And so in that they extract these statistics, they are informative about the structure of representations that is possible. Doesn't say the nervous system does it exactly like that, and it also doesn't say that that's the process of how nervous systems do that. For instance, learn, like in perceptual learning, when you learn to discriminate a visual category, like in childhood or when you're trained in the laboratory. In fact, there's a whole field of work looking at that, at such processes, and it's much more subtle and complex. It summarizes more something like what happens in evolution, perhaps, but not as a process, just as the outcome, right? So that's the main use of these kind of networks. So here an example from work that's interesting to me as well, again from McClellan's group with someone called Rogers, where they are looking at how people classify certain objects, and they're reconstructing a metric of how similar these objects are based on dimension scaling. So how can you order these objects in a way that somehow minimizes some measure, and then training a neural network with a certain structure can account for that metric structure. Then you have learned something about the structure of representations, even though the learning of the network does not reflect how, for instance, children learn these categories. That's a different issue. So this much I want to say about connectionism, and maybe even more briefly about computational neuroscience. So in a sense, computational neuroscience is a branch of connections, but it's not quite fair to say that, because this technique of using the so-called learning rules to extract properties that reflect statistics, that's not actually what computational neuroscience is really about. It's just that they also use neural networks, but they are taking the neurophysical basis of these much more seriously. For instance, the fact that they have synapses, synaptic dynamics, they have activation dynamics, they spike, that certain neurotransmitters can modulate the synaptic efficacy and things like that, and then try to account or link that to functions. So I'll give you one example. This is Daniel Dostowitz, who used to be at the Rosen University in past years, and is now in Mannheim. So he worked, for instance, on models of working memory for a while. Working memory is in some sense considered to be neurally done by sustained activation. That is, if you get a certain input or a certain task, and you have to hold that task in your mind before you can actually act on it, that then neurons that are involved in that task would keep firing, even though there is no sensory input to those neurons anymore. So they keep firing just by virtue of the connections among these neurons. So here's an example of neurons in this holding period, just firing, even though they don't get any external input in this period. I don't want to explain all the details of that. These little lines here are spikes of these neurons, and the lines are different trials. See, they're always spiking in this holding period. And so there are models of that. I'm also engaged in doing that. They're all sort of based on self-excitation, that a population of neuron has recurrent connections where once they fire, they provide input to their neighbors in various forms, and therefore once they fire, they keep firing. And so the computational neuroscience folks would really try to link this performance of the system, that the extent to which it can keep activation alive after the stimulus was removed, to do that as a function of neurophysical details, so for instance, cell types, dependence on timescales, dependence on neurotransmitters. For instance, here the effects of dopamine on that function, dopamine as modeled, where you know how synapses depend on, for instance, the concentration of dopamine, and then they would link that to neural manipulations where you can vary dopamine levels in various ways in animals, for instance, or even link that to disease, where you would say that someone with dopamine deficiency, for instance, could I predict characteristic failures of that person's working memory, for instance. That's sort of an example of that kind of research problem. So seeing a link between function and sort of constraints at that micro level. It's maybe some debate about whether that's really been effective, but there's a research field right there. That's what I want to tell you. Okay, so I want to circle back to the original question. So, are these, if you make these models at different levels, can you say that, for instance, the computational level is really about laws, and the implementation level is really like description, like biology? Actually, I don't really think that that is clear. So as I hinted, these levels are not so clearly defined. So I think the tension between these epigenetic transitions and neuroscience, cognitive science as sort of an interface between neuroscience and behavioral science, I think the tension doesn't go away easily. And so I've argued that it's actually not a priori clear which level, at which level the laws reside. You actually have to find out about that. It's an empirical question. So the laws are irregularities, right? They are any form of constraint that says only certain processes or patterns are possible, and at which levels these laws can be found, you have to find out yourself. That's actually exactly how it works in physics. In physics, there are, for instance, in physics, some of you might know that there are acoustic phenomena and there are electronic phenomena. And it turns out the acoustic phenomena have to do with the motion essentially of the nuclei of the atoms involved, because that's where most of the mass is, all about the masses. The electrons really contribute very minimally to acoustic waves, while the electronic phenomena have to do with the electrons circling around in these clouds around the neurons and excitations that happen in them, and they are separated by time, orders of magnitude in time scale, for instance. And so you could say that the right level to look at electronic laws is the one of electrons. And actually, it's a little bit more subtle than that. But for instance, for semiconductors or for, let's say, for metals. And then if you look at acoustic properties, it's essentially just high frequency mechanical deformations, then you can say what the right level for that is. That would be sort of a metaphor for what I'm talking about. So I've personally argued for instance, in a recent opinion piece that neuropopulations are really the level at which regularities that we observe at the level of behavior and thinking are reflected. So populations being still small, populations much smaller than areas than you see in a brain scan, but certainly not individual neurons. So no evidence for the discreteness of neurons or the discreteness of firing actually playing a role. And in my other lecture course, I'll talk about that. So we call this dynamical field theory. Some of you are listening to that other lecture. Actually, this was from last year. This is not true anymore. So we're talking about particular constraints there, stability, instability, attractors, and so on. These are attempts to capture regularities of thought, of cognition, and we're actually seriously doing a program like that. So that's the other course that is going on here. And so in hindsight, so overall, if you look at the whole picture, I've tried to argue that mathematical models are important to transform intuitions, mental images, verbal theories into precise, sharp, precise theoretical statements. When they are compared to data, especially when it's done quantitatively, they can give rigorous feedback about these concepts. They can uncover problems, overlooked processes, maybe even also sometimes identify parts of an account that are not necessary to account for the data. So the way that models fail are very useful, but it's not, and that shows that the models are actually just the tools with which this sharp thinking that I would call theoretical thinking, that conceptually precise thinking that is testable, is, that's a tool with which you do the tests. But the models themselves are not really the result. When the model works, it just says there is no bug in this thinking as far as the current state of the art can determine, and that's good. It's actually pretty much like the laws of physics. We can't be sure that these laws of physics will turn out all to be valid. We've often found that there is actually a deeper theory, and the other theory, your early theory, only results as a limit case under some special cases, but in general, it's wrong. And that might be true for pretty much all models, and the models are therefore just the tools to recognize when such steps have to be made to generalize the theories. So in that way, models make conceptual commitments explicit, which is, and the theory is about that. It's about being able to express such constraints and make them explicit. In computations, maybe the metaphor that's very strongly used, it's ironic that we call these computational, these three lectures are the computational lectures, right? And it's used, and I just do this as a gesture to everyone. I think it would be really better to talk about this as theory, but there are other people who think theories are just verbal stories as well. So it's mathematically precise theories, and we call these sometimes computational, but the word computation actually has additional baggage coming with it, both historical and conceptual, and so I don't actually like that so much. I really would say that it's really just a rigorous, mathematically precise way of theoretical thinking in cognitive science. And so my last point, I don't repeat again, I just said that ultimately to find out what are the right levels at which we want to model, what are the right kind of models, that is an empirical, a scientific question that we have to find out. There is no a priori reason to think that individual neurons are the right level, or modules of impenetrable function are the right level. We have to find out, and it might be different for different kinds of laws. So what does it mean to understand the brain? I want to end on that, and I have this image of possible minds. I used to teach Neuroscience graduate school here, a lecture, not exactly like that, but more like closer to neuroscience, and sort of then in the end I told them, you experimentalists always complain that it's so difficult to measure. Just assume for the moment that you had everything about a brain that is measurable, or that if just theoretically, you would have every synapse, every neuron's activation, every neurotransmitter's concentration, and so on. Huge computer database, and everything is in there. It somehow magically was measured. Maybe even you have the muscle activation and all that. So would you then understand the mind? And of course, not directly, right? And more practically, you have multiple brains, different computers, and they're not exactly the same, we know, as I said initially. So what would it mean to understand these? And so one thing is, if one of those brains was fake, now somebody actually just typed in all that data, which would have been a lot of work, would you be able to tell which one is fake? Which brains are possible? That would mean that you have captured the constraints. What kind of variation is possible? What kind of variation is not possible? That is, where there has to be covariation. Because it's not a practical method, because this would just depend on how stupid the person is, or how lazy, who typed in the brain. If all the parameters are set to 0, then you would easily identify that as a fake. So if the fake gets better and better, and that would mean somebody who understands the laws of the brain could make a very, very good fake that you would not be able to pick out. And then you have understood the brain in a sense. Right? Possible brains as a theory. So with that, I would like to close